All right, guys, it's Ripley. Welcome back. You have reached the summit. In an introductory statistics course, this is it. We're going to start testing hypotheses or testing claims. And these claims, what we're going to go over is so cool and so useful, and it really builds the foundation for all of statistical theory and statistics used by researchers. Let me explain this as simply as I can. If you take a die and you roll it and a 6 pops up, is anybody surprised? The answer is probably no. If I take a die and I roll it again and another 6 pops up, is that unusual? Are you surprised? No. But what if I take that same die and I roll it, say, 10 times, and all 10 times you get a 6. Now your spidey sense is tingling, isn't it? Something ain't right. Now, is it possible that you could take a die and roll it 10 times and get all 10 rolls to be 6s? Of course, it's possible. But is it probable? Well, I mean, let's just look at the probability of it. The probability of 10 6s, right? They're independent rolls, so it's 1/6 raised to the 10th, or 1/6 to the 10th, right? Which is, I'm going to throw it on my calculator, divided by 10 to the, 6 to the 10. I'm going to screw that up. 6 to the 10, and guess what? It's 0.000000000, 1, 2, 3, 4, 5, 6, 7, 165. That is highly improbable, okay? Now, what does that mean? It means that since the probability of this roll is so low as to almost be 0, we have to conclude that something is wrong with the die. All right? Now, this idea, while dramatic and a bit of hyperbole was used to demonstrate, is exactly the idea behind testing a claim using statistics. Now, just like we build confidence intervals around proportions, around mu, and around sigma squared, or sigma, right? We're going to do the same thing, only we're going to test claims around proportions, means, variances, and standard deviations. Really, what we're most concerned with is these two guys. And the hard part is to sort of get your brain wrapped around which method that you're going to use, because there are multiple methods in doing this. But some are more confusing than others. For some people, certain methods work really, really well. All right? And I'm going to go through all of the methods. By the time everything is said and done, we're going to talk about all of the methods, all of the statistics that we use, all of the formulas that we use. Okay? So it's official. Welcome to the party. So the first thing that we need to be able to do if we're going to test hypotheses is we have to learn how to write hypotheses. Okay, so we got to learn what that entails. Now, there are two kinds of hypotheses. There's something called the null hypothesis, and then I'll just abbreviate that. And this is written, we're mathematicians, so we're lazy and we need shorthand. And there's something called, this is written as H sub 0. And then you'll see this written as the alternative hypothesis, lazy today. And sometimes you'll see this written as H sub A, but usually you'll see it written as H sub 1. All right? Now, there are only two hypotheses in hypothesis testing. Now, I'm going to show you this. The best way to do these is to demonstrate. The one thing that's the most important that you wrap your brain around is the fact that the null hypothesis always contains the equality. If it's got an equal sign in it, it goes with the null hypothesis. So the null hypothesis says, I'm going to have an equal sign in this. Now, I'm going to read you a couple statements, and then we will develop the null and the alternative hypothesis for them, okay? This is a claim. We're going to test a claim, and we're going to write the hypothesis for this. 3/4 of all adults use the internet. That's my claim. So we're going to write up the claim, and we're going to do 3/4 of adults. I don't know why I'm slashing my fractions like that. It's silly. Adults use the internet. All right? Now, I don't know if it's accurate or not. I don't. To be honest with you, I don't really care at this point. 3/4 of adults use the internet. Now, the first thing that we want to talk about here is, what are we testing? Are we testing let me change colors. Are we testing the mean? Are we testing a proportion, or are we testing a variance? That's the most important thing. And really, that's all that you have to worry about, is which of those three things are we testing? Well, look at it. It's 3/4 of adults use the internet. Think of this as 75%. Think of that as 0.75. So what we're doing is we're doing a test on the parameter for proportion. So watch this. All I do is I'm going to write up my null hypothesis and my alternative hypothesis, and here they come. My null hypothesis is that the parameter, P, equals 0.75. Now notice, it says, in other words, basically this statement right here can be distilled down to the population proportion of adults who use the internet is 0.75. Now, notice that the null hypothesis contains the equality. It always does, and it always has to. The alternative hypothesis, well, what is the complement of P equaling 0.75? Well, it's simple. It's P doesn't equal 0.75. That's it. Those are my hypotheses. Either this is true or this is true. Statistics doesn't concern itself with, well, what about it could be 0.75 or it could be 0.8 or maybe 0.67. No, it's either 0.75 or it ain't 0.75 as far as us testing this claim is concerned. All right? Now, let me read you another one. All right? The average amount of garbage that households use. Let's write this up. I'm going to get back to my black. Back in black. Sorry. Average garbage. Wow. Sorry. Let's try this again. Average monthly garbage. I'm not going to write that in. Garbage households use. Households use is less than 30 pounds a month. Month? Yeah, what the heck. Less than, or maybe a week. Who knows? Doesn't matter. Is less than 30 pounds. All right, that's my claim. Somebody comes up, yeah, the average household burns through 30 pounds garbage a week, a month, a year. We know that's probably not true. Okay, now we're going to test that claim. We're going to go out and we're going to say, okay, well, let's see what that really entails. All right, so I got my null hypothesis and my alternative hypothesis. Now, what are we testing? Is this a proportion? Is it a test on average, on mean? That's a nice piece of information right there, isn't it? Or are we testing variances? The answer is we're testing the mean. So the null hypothesis always contains the parameter and the equality. So we're going to do mu equals, and mu is something else. Well, notice how it reads. The average garbage households household uses. Wow. Uses. Wait. Average uses is that makes no sense, but you know what I'm getting at. Is less than 30 pounds. So I know for a fact that the alternative hypothesis, because this is less than and doesn't contain an equality, is mu is less than 30 pounds. Now, what is the complement of less than 30 pounds? It's greater than or equal to 30 pounds, but we really don't care about the greater than part. We really just want to test whether it equals 30 pounds or not. It's either, notice we draw this sort of line in the sand and we say mu is less than 30 pounds or mu is equal to 30 pounds. Now, the sticklers among you might say, well, Ripley, I want to write greater than or equal to. And you would be right, because now we've got a truly binary situation. I'm either less than 30 pounds or I'm greater than or equal to 30 pounds. But sometimes, most often, you'll see this simplified as just equals. Don't panic when you do that, okay? Let me read you another one. The human body temperature is 98.6 degrees. Human body temp. So somebody comes up and says, hey, the human body temperature is 98.6 degrees Fahrenheit. That's a claim. It may or may not be right. Well, what are we testing? What claim are we testing? Are we claiming, or excuse me, are we testing a claim about a proportion, about a variance, about a mean? Well, clearly, I mean, if you really think about this, human body temps are going to be all over the place, right? I mean, take your own temp 6 different times a day, and you're going to find out that your temperature, your body temperature varies depending on what you're doing, depending on the temperature of the room, depending on whether or not you're sick, et cetera, right? So really what we're doing is we're testing an average. All right, now let's see how this guy plays out. The human body temperature is 98.6 degrees. So we're making a statement about the parameter mu. All right? I believe that the average body temperature is 98.6 degrees. So what is the alternative? Notice I didn't make any sort of claim about being greater than or less than or anything like that. I simply said human body temperature is 98.6 degrees. Well, that implies that the alternative hypothesis, which always contains the inequality, right? Less than, not equal to, this guy's going to be not equal to 98.6 degrees. You see how that works? All right, let me give you one more. Excuse me. How about this? Polygraph results are correct more than 80% of the time. Polygraph, so you know, lie detector tests, right? Polygraph results are accurate more than, now hopefully your spidey sense is starting to tingle here, more than 80% of the time. All right, so we have a null hypothesis which contains the equality. We have the alternative hypothesis which contains the inequality and doesn't have an equal sign in it, right? What are we testing? What is this? Is it a mean? Is it a variance? Is it a proportion? Yeah, it's a proportion. It's a percentage, isn't it? So I'm testing this guy over here. So I come back over here and let's see, I'm going to have a P here and a P here. I know the jokes write themselves, quiet. Now look at this. Accurate more than 80% of the time. That doesn't have an equality in it. That's a strict greater than. Okay, so it's going to be P is, my alternative hypothesis is P is greater than 0.8. Well, what's my null hypothesis? If I wanted to, I could write this up as simply P equals 0.8. Even though, 0.80, even though parenthetically speaking, I guess we could think of this as, is actually, it could be less than or equal to 0.8. And that gives us this nice complementary relationship between our null hypothesis and our alternative hypothesis. You want to get in the habit of reading claims and immediately being able to flop into, okay, what's the null, what's the alternative? And not only doing it in this class, but every time somebody, you know how they say, what is it, 56% of all statistics are made up on the site or on the spot, right? That's a claim. You could test that claim. You know what I mean? You could actually go around and grab people randomly and have them quote a statistic and whether or not it was made up or not. Okay? There's lots of fun ways. There's tons of fun ways that you can test claims, and actually we're going to do a bunch of that in this class. But the first thing you have to be able to do is write the null and the alternative hypothesis. Okay. And what I'm going to do is I'm going to play with you guys just a little bit. We're going to mess with this one. We're going to test this. We're just going to work with proportions for now. All right? These two guys. All right, so we'll transfer them over here. We'll deal with them one at a time. So the first thing that we're going to do is we're going to deal with the claim that 3/4 of adults use the internet. All right, and we've got our null hypothesis, which always contains the equality, and we're doing a test around a proportion, so 0.75 or 3/4. And our alternative hypothesis, since I don't have any other information, it's either equal or it's not, and we're going to go not equal to 0.75. Now, we're going to get into this in class, what exactly alpha is, all right? But I think you're going to start being able to figure out, based on what we've messed around with alpha before, what it is. But I'm going to test this at alpha equals 0.05. And I'm going to make up some information, okay? First and foremost, I'm going to say that we took 3,011 people, all right? And we asked them, do you use the internet? Okay? And let's say, so I got n equals 3,011. Let's say that 73% of them, so 73% said yes. All right? Now, what I want to know is this claim validated with this information? Now, bear with me for just a sec. We're gonna kind of explore this problem and take our time with it. And I'm going to show you a few ways to play with it. All right? Now, first things first, let's identify what we know. I know that p hat, because remember, we took a sample of 3,011 and approximately 37%, this could be off by some decimals, said that yes, they use the internet. Now, you may automatically say, well, Ripley, okay, this is different from the claim, but the question is, like the die that I rolled 10 times and got all 6, is it far enough? Is it different enough? To be able to answer that, there are 3 different techniques that we can use. All right, I'm going to walk you through all 3 techniques. And we're going to start with the confidence interval. That's our good friend. Now, the confidence interval can be used because this is what is referred to as a two-tailed test. And the reason it's two-tailed is because this is a not equals. If this were, remember back here, if it were a less than, if it were a greater than, or it were a less than, it gets harder to use the confidence interval. And I'll explain why down the road when we start playing with those as well. All right? So the very first thing that we're going to do is we're going to build a confidence interval around this guy. All right? That's the first way to test it. So we're going to pick alpha equals 0.05, which implies that we're going to do a 95% confidence interval around. This is the nice little boilerplate way to start. Around P. And we're going to see if 0.75 fits in that. Well, let's say if you remember your formula, the confidence interval around P was what? You take P hat, right? And you subtract the error term. And what was the error term again? It was Z sub alpha halves times, and then it was the square root. If, remember, we're assuming that this is our parameter. So I get to say 0.75 times 0.25. Remember, if we didn't, then we would assume that both P and Q are 0.5. And I divide that by N, which is 3,011. And that's going to be the left bound. On the right, it's going to be P hat plus Z alpha over 2 times the square root of, ooh, I'm going to run out of room over here, aren't I? Times the square root of, okay, dang it, everything's coming unwound. 0.75 times 0.25 divided by 3,011. All right, now we have to check a couple things first. Remember, when we deal with proportions, what we're really dealing with is kind of a binomial setting. And I know it's easy to screw those up, but one of the assumptions for being able to deal with this is to ensure that NP and NQ are both greater than or equal to 5. Well, that's easy to see. I mean, if I take 0.75 times 3,011 and 0.25 times 3,011, you're darn well sure we're going to be greater than or equal to 5. So we can cross that off. That's one of our assumptions when we're dealing with this. Now let's actually build out our confidence interval and see what happens. I take P hat, which is 0.73, right? Minus. Now, do you remember what the Z alpha over 2 was for a 95% confidence interval? Well, that was easy, right? It was 1.96. Let's make sure. Let's back up just in case. If I stumble over here, I want to get to my Z table and I want 0.025. Remember how this worked? I could go 0.025. Where's that guy? 0.25. 0.025 right there is negative 1.96 and positive 1.96. Because remember, sample proportions distribute themselves normally. Sampling distributions for proportions distribute themselves normally. So I got 0.73 minus 1.96 times the square root of 0.75 times 0.25, just building the confidence interval and checking to see if this guy is in there. Divided by 3,011. and 0.73 plus 1.96 times the square root of 0.75 times 0.25 divided by 3011. And that's going to be my interval. So using my fancy schmancy calculator, I really need to get one of those calculator programs where I can do this on the computer screen, but so you guys could catch all my ding-dong errors. So 0.73 minus 1.96 times the square root of 0.75 times 0.25 divided by 3011. In paren, I think I'm good there. I end up with 0.715 on the left, and if I hit second entry and change my minus to a plus, which saves me a boatload of time, I get 0.745. Uh-oh. Wait a sec. Notice this 95% confidence interval, which really tells us we're 95% confident that the mean should be in there. Now, here comes the lawyer math. Wait a sec, but we're only 5% confident that we could make an error. I could actually have chosen, just by random chance, that these 3,000 people were way too low. But we don't care about that, all right? We hope that everything went well and that our data values are valid, which they are as long as they were collected randomly. All right, now we're going to write this up. Since 0.75 is not, now this is fancy mathematics, since 0.75 is not in the confidence interval from 0.715 to 0.745. Now here's where we get into the lawyer speak, all right? There is evidence that the population proportion for internet users, for adult internet users, isn't 0.75. Now, why do we get to say that? Because what we actually did, since the null hypothesis isn't in this, we actually rejected the null. We rejected the null hypothesis. It doesn't live in this confidence interval. There's no way, if this confidence interval is correct, which we hope, I mean, we're 95% confident that it would contain the mean, well, then this guy better be in it. If it's going to be, you know what I'm saying? If 0.73 isn't different enough, then 0.75 needs to be in this confidence interval. And therefore, we're going to reject the null. Now, this method is using confidence intervals. And remember, it only works if we have a not equal to right there. If it's anything other, it's not going to work. All right, now, we're going to do an entirely different way of testing the hypothesis. Okay? So here it comes. Kind of buckle yourself in. There's going to be two more. But they're not, initially when you start playing with these, they can be a little counterintuitive, but don't be afraid. So the first thing we're going to do is we're going to test the null hypothesis that it's 0.75. Now we know from the confidence interval that it already can't be that. All right? My alternative hypothesis, this is equal to P, and this is 0.75 is not equal to P. Now, what we're going to do here is find what are called critical values. And we've talked about critical values before. Values, and alpha equals 0.05. Now, what 0.05 is in this case, and I know this is going to sound redundant because we already found, quote unquote, the critical values, but watch how this works. 0.05 is kind of the allowable probability of failure, but what it really says is we're not going to let this, remember, p hat equals 0.73 and n equals 3011. We are not going to let 0.73 drift far enough away from 0.75 that it ends up out here in crazy town. If after I take a value, a test statistic, and I'll show you the test statistic here in a sec, If my test statistic that I take ends up too far, if it ends up in this is called the critical region. Critical region, as is this, same thing, I'll call this the CR, okay, or the critical region, then that means that 0.73 was too far away from 0.75, and it's not going to work. Excuse me. The test statistic that we're going to use for this, let's get back to black, the test statistic, so the test stat, it's just Z, and all that it is it's p hat minus p divided by the square root of PQ over N. Okay? Now, you may say, whoa, this looks kind of familiar. Well, it actually comes from the fact that, remember, my z-test for my binomial was, what was it? It was, think about it. It was, remember we had NP, x minus mu, which was actually n times p hat, minus n times p divided by root n pq. If I divide everything by n, then I end up with p hat minus p. If I divide this by n, I end up with the root n in the denominator. So that's where it comes from. It's nothing fancy. And we don't have to worry about the whole central limit theorem thing because we think of this as that's all encompassed in this. Now, remember, if alpha equals 0.05 and we're on the standard normal curve, then that implies that this area over here is going to be 0.025 and this area over here is going to be 0.025 because of, whoops, that's supposed to be a 5, because of the symmetric property of the standard normal curve. Well, we already know what this critical value is. It's 1.96 and it's negative 1.96. Those are the z values that in this case, they're the line of demarcation between if I get some weird value in here, okay, that's allowed. I'm going to allow my value, my test, my point estimate to fall in here. But if it falls outside of there, something is fishy. I'm rolling the dice and I'm getting too many 6s. So watch how this works. It's actually very simple. I just take z equals, I go 0.73 minus 0.75, and I divide that by the square root of 0.75, just like we did before, times 0.25 divided by 3011. And let's watch what happens. So let's see, what do? I'm going to take negative 0.02, so negative 0.02, and I'm going to divide it by the square root of 0.75 times 0.25, and I'm going to divide that in there by 3011. I really do need to get that thing, don't I? And this is, watch this, negative 2.53. Which means that for this test, right here, this point estimate, where did it end up on the curve? Well, here's negative 1.96. This is the line of demarcation. If you cross this line, something is fishy. And sure enough, I crossed that line. This right here is my z-score, which is negative 2.53. Alarm bells are going off. Well, we knew they were going to go off because when we did the confidence interval, we were screwed. Guess what? We reject the null. We will either reject or accept the null. Think of it as, again, it's a binary situation. We either accept this or don't. And in this case, we throw it out. And again, we wouldn't write up the same write-up. In class, we'll go over how to write these write-ups up because this write-up has to do with the confidence interval, but it's very similar. There is evidence that the population for proportion for adult internet users isn't 0.75. Now, I'm going to do it one more time, and we've actually done the heavy lifting for the proportion. Watch how this works. I got to remember that z-score. The last way to do this is, I'll go ahead and change it up here, is something called a p-value. And I want you to notice all three of these are going to give you the same thing, or are going to give you the same conclusion as far as accepting or rejecting the null. But the thing that's most important is you basically get to pick it. You get to pick your favorite. Now, I'm going to force you to do certain hypothesis testing with certain ways. With either the critical value, remember this right here is called the critical value method. This is the confidence interval around the proportion. And then what we're about to do is called the p-value. But again, the p-value is already, if you've already done the critical value, then the heavy lifting is already done. Your computer does it with p-values. Now, the p-value is actually real simple. All you do is find the z-test statistic, right? Which we know was 0.73 minus 0.75 divided by the square root of 0.75 times 0.25 divided by 3011. And we ended up, what was it? I forget what it was. 2.53? Was that what it was? I'm getting old. Negative 2.53. Negative 2.53. Now, what does that mean? It means, remember, sample proportions, unbiased estimator. Not only that, but they distribute themselves on a normal curve. Wow, that was a train wreck. However, in total absence of critical values, we don't even have to worry about them. With p-value, what we're going to do is we're going to find the probability that we get a value at least as big. Okay, so my z-score or my z-test statistic was negative 2.53. All right, now that tells me that my p-value is the following. I'm going to go over to my curve. All right, let's get over to my curve. We're on the standard normal. And we're going to figure out, let's see, what do we say? Negative 2.53, so negative 2.5 and negative 2.53, 0.0057. Remember, it gives us all the values to the left. So 0.0057 gives me let me double check. I'm getting a little punchy. All right, so back here, that implies that the probability of getting a value at least as extreme, in other words, of ending up out in this crazy land, is 0.0057. That's a very small amount. But the question is it small enough? And the answer is yes. All right, here's why. Now think about this. I'm going to redraw my curve because that one's just horrific. Because it's two-tailed, that means that I'm going to have a couple of, now this is really easy to explain, especially once you've seen critical regions. What I'm going to have is I'm going to have a 0.025 on the top end, and I'm going to have a 0.025 on the bottom end. All right? Now remember, the null and the alternative, my null hypothesis was that p equal 0.75, and my alternative hypothesis was that p wasn't equal to 0.75, which means that I can miss on either side. Okay? My p-value ended up being, now that remember, this p-value is different from, this is actually a probability value. It's the probability that I get a value at least as big. It ended up being 0.0057. All right, because when I did my test statistic, I need to change. I know that I'm repeating myself, but trust me, it's a good thing. My z was negative 2.53. All right. Now remember that 0.025 came from alpha divided by 2, because alpha divided by 2 was 0.025 because alpha equaled 0.05. Now this happened because of this inequality right here, because it's not equal to. If this p-value is less 0.0057, because it's less than 0.025, which would be defined by this critical region right here, this critical value right here, which we knew was negative 1.96. But remember, we're ditching the whole critical value thing, although we'll keep revisiting it over and over and over. Since 0.0057 is less than 0.025, we're going to reject the null. In other words, the probability, the likelihood that I get a value at least that extreme, that I get a 0.73, which to us may seem, well, that's not very far off. Yeah, but taken in context, think about that. The number of people that were surveyed, the law of large numbers tells me I better start heading for 0.75. The problem was I didn't get close enough to 0.75. So the probability that I get this 0.73 or a value that's at least extreme is only 0.0057 or 57 out of 10,000. Now we have agreed that the acceptable amount of probability we're allowed to have is 25 out of 1,000, or 0.025. And therefore, we reject the null. There's enough evidence to reject the null because of this p-value right here. So, in summary, and we're going to do one more of these guys. I know that you guys have hypothesis testing takes a long time. So these are going to be some pretty long modules, but don't panic. We'll get you through them all. In summary, there's 3 ways to test this kind of null and alternative hypothesis: equality, inequality. You could do a confidence interval, you could do critical values, and then you can do p-values. All right? Now, take a break. Take a deep breath, walk it off, get something to eat, hang out with your friends, do whatever. Excuse me, because what we're going to do is we're going to do that other proportion one. We're going to test that other claim with some data. And that guy, where was that? 0.75. We're going to do this one. Polygraph results are accurate more than 80% of the time when you come back. All right, take a break. All right, I hope everybody isn't getting too frustrated. Welcome back, by the way. Really, the best way to get good at these types of things is to just work a lot of problems. Your brains will wrap. It's real tricky right now. I know it's pretty abstract right now, but we're going to work some problems. We're going to do a ton of problems in class, and by the time we're done, I guarantee you're going to get it. All right, so here we go. Polygraph tests are accurate more than 80% of the time. So the first thing we always do is we write our null hypothesis and we write our alternative hypothesis. Well, again, we're doing we're testing a claim around proportion, and this says more than, which implies my alternative hypothesis is going to be p is greater than 0.8. My null hypothesis, I could write it as less than or equal to, or I can simplify the process and say that it's equal to. To be honest with you, when I first started learning, I kind of parenthetically thought about this like that. Okay, you know, it's like less than or equal to. I wanted that thing to be perfectly binary. All right. Now let's make up some data. Let's say that they gave 98 lie detector tests. Okay, and you know, they're not for real lie detector tests. You know, it's not like they tested prisoners because they wouldn't really know if they were lying or if they weren't. And let's say that out of the 98, 80 were accurate. And what do we got? 18 not accurate. All right? So first thing we better check is NP and NQ greater than or equal to 5. Remember that? Because it's kind of like a binomial deal. Should be relatively easy to see that. 0.2 times 9.8 is going to be close to 20. 0.8 times 9.8 is going to be pretty close to 80. So I think we're in good shape. So check. All right. Now we're in business. Now here's a problem. Because of this alternative hypothesis, instead of being two-tailed, this is called a one-tailed. And any time that you have a one-tailed, we can't use, this implies no confidence intervals. You can only use confidence intervals on two tails. Hopefully you can figure out why that is. Maybe not. All right, but that's okay. You'll figure it out down the road. Now the other thing that we're going to need to pick out is we're going to have to pick out an alpha level. All right, we're going to figure out what is an acceptable level of variation. In other words, how much probability that we're going to be dead wrong, that we're going to assume the exact wrong thing, are we going to allow? Again, the union standard is about 0.05, is at 0.05. So alpha equals 0.05. At this point, we are committed. Now, if we wanted to, we could go 0.01. We could go 0.1. But 0.05 is going to be recognizable by a lot of people, and they're going to be like, okay, this guy or gal knows what they're doing. Now, again, we can't do confidence intervals. So let's go with, we're going to do critical. Let's do critical value first. Down the road, I'll switch these around and we'll do p-values first. All right, remember, sample proportions distribute themselves normally. They're an unbiased estimator. All right, so notice that this is a one-tailed. Now the question is where does the tail lie? In other words, where is this critical region going to lie? All right. If my claim is that they're more than 0.8, then what I have to do is I have to prove beyond a shadow of a doubt that my value is going to be way or enough above 80% to be able to throw out the null hypothesis. The null hypothesis always contains the equality. So what that says is I want the value for 0.05 right there. That's what alpha is. If alpha is 0.05, then I now want the critical value that cuts this off. Because if I end up with a critical value inside of this region, then that is far enough away from my mean or my assumed population proportion of 0.8 to say, hey, something's fishy. Now, I'm going to show you how to find this. So, you ready? Well, I'll stumble up here. Let's go critical value, and it's going to equal. Now, remember, it's on the normal curve. So that's nice. That's a good piece of information. I'm going to escape out of here, get rid of this. I'm going to head over this way. All right? Now, there's lots of ways to do this. Remember, it's a one-tailed distribution. So what I'm looking for is I'm looking for one of two things. Let's real quickly. Let me bring that back up. A lot of times students will say, well, Ripley, how do I know which side the tail is on? Well, notice this guy right here always points in the direction of the tail. It's a greater than, it's a greater than 0.8, but the inequality points in the direction of the tail. So if it were a less than, the tail would be on the left. All right? So there's lots of ways to do this. If I want to get fancy, I can think of this as being, there's 0.95 to the left of whatever this critical value is. All right? So I'm going to head over here because my chart only gives me values to the left, and I'm going to look for 0.95. So check it out. Let me see if I can get the top here so we can see it. 0.95, let's see, 0.945, 0.9505, and I am between 1.64 and 1.65. So what I do is I split the difference and say that the critical region for that happens at right here. This is my critical value, and it's going to be 1.645. Now, in summary, that is the line of demarcation. If my z statistic, if my test statistic gets into this area right here, remember we called this the critical region or CR, then I am too far away from 0.8 and I can reject the null hypothesis and accept my claim. I reject the null. There's evidence that the null is wrong. If I end up in here. If I don't, there's not enough evidence. I can't do anything. Okay? So let's kick back over into this mode and let's remember our formula. My critical value is at 1.645. Now, let's test it. Well, the first thing I need to remember is z is equal to p hat minus p over the square root of pq over n. So let's see. I need p hat, don't I? I know what p is. Let's write everything up. Keep it simple. P is 0.8. That's in the null. Q is 0.2. N is 98. And p hat is going to be what? Well, it said that 80 out of the 98 were accurate. I know that's a little bit confusing because of this 0.8 and this, but we're not afraid, right? 80 out of 98, which is equal to 80 out of 98, and that's equal to 0.816. Now, 0.816 is bigger than 0.8, but I hope you're starting to get the idea here. Is it big enough? Okay, well, let's figure it out. 0.816 minus 0.8 divided by the square root of 0.8 times 0.2 divided by 98. All right? So 0.816 minus, what do we got? We got 0.016. Let me throw it in my calculator. 0.016 divided by second square root of 0.8 times 0.2 divided by 98 in paren, and I end up with 0.396. Whoa, how anticlimactic. Look at that. 0.396. That's the z-value, which gets me right here. I mean, think about it. On the standard normal curve, this 0.8 turns into a 0. So 0.396 is like right here. That is not acceptable, right? It's not enough evidence to reject the null, which implies, think about that, which implies that the claim itself is wrong. So because, now we're going to write this up nice and clean and nice and pretty, since 0.396 is less than 1.645, there is not enough, we're going to keep it simple, not enough evidence to reject the null hypothesis. It appears the claim is wrong. Is dead wrong. All right, the evidence says it's wrong. Okay, now let's prove it with p-values. So this was the critical value one, right? Now we're going to prove it with p-values. So the cool thing is, again, with the critical values, I've already done the heavy lifting. So now let's do it with p-values. What was my test statistic? What the heck was my test statistic? I know that z equaled what was it, 0.318? 0.396. Let's go back. So my my charts aren't going to give me that. So really, my z is equal to let's go 0.40, because I have to round, because that's how my chart works. I stumble back to my chart. All right, I got a z value of 0.4. You know what? Before I do that, let's see. Think about what's going on. Let's draw our curve here. My critical value, well, I'm not even going to put the critical value. All right, when we go to the standard normal, I get 0. I'm going to get a z equals 0.4, and now what I'm looking for is the probability of getting values at least as extreme. So I go back to my chart, and I'm looking for, the problem is, what are we going to do? Let's look at it. I need to get out of my own way with this here for a second, don't I? Go to z equals 0.40, right? Wasn't that it? Well, z equals 0.40 gives me a probability of 0.6554. All right, let me get my paper back up. So 0.6554. So that tells me that everything to the left over here is 0.6554. If this is 0.6554, then isn't this guy right here, which is the probability of getting values at least as extreme, of, what is that, 0.3446, 0.3446. So my p-value equals 0.3446. Now I want you to notice something here. Remember when we had the two-tailed thing, I actually had to take alpha and divide it in half. I had to cut it in half. But because we've got a one-tailed situation going on here, I don't have to cut it in half because I can't miss on both sides. I'm only worried about missing on the high side. So here's my p-value, 0.3446, since 0.3446, which is the probability of getting values at least as extreme as I got. The probability of getting that 0.81, which was our test, which was our sample proportion, well, that's 1 in 3 times. That's to be expected. Since this is greater than alpha, remember, if it was less than alpha, we reject, but since it's greater than alpha, we do not reject. And that's it. That's all there is to it. Okay. Walk it off. When we come back, we'll do some hypothesis testing around means rather than around proportions. All right, I'll give you test statistics and all that good stuff.